Okay, welcome. This is Unit 1, Day 1, Introduction to Limits. This is for people that may have missed class or perhaps just got moved into the class or just wanted to kind of revisit it as a way to refresh their memories. Okay, so here we have the limit as x approaches c of f of x equals L. So the important thing to keep in mind here is, again, you read that as the limit as x approaches c. So we're saying what's happening as x gets closer to some value. What is the function doing? AKA, what is the y value? That's what you're looking for when they ask you for a limit. You're saying, what y value are you approaching or getting very close to? So we need to keep in mind that a limit exists if that is a real number, and we'll talk about what it means for a limit not to exist later. And f of x gets close to L as x gets close to, and again, that means approaches that c value. So taking a look at these next three examples here, basically it's asking you to find the limit as x approaches 1 for f of x, g of x, and h of x respectively in each of these piecewise functions. So here, the limit as x approaches 1 of f of x, that's saying from as x, right, is getting closer to 1. So here's x equals 1. So as you are kind of going along this function, as you're getting closer to 1 from either direction, what y value are getting close to? So for example, at, x equals a half, maybe you're at 1.5. At x equals 1.75, maybe you're at, as x equals 0.75, your y value might be 1.75. And at 0.9, it looks like this is going to be 1.9. So again, you're getting closer and closer to the y value of 2, so that's how we say the limit there equals 2. Notice that the whole there does not affect the limit. It has no impact. And now we'll go on to the second one. So for g of x, we have our x values getting closer to 1 on either direction. If you're on the actual function, your y value is getting closer and closer to 2. And again, just imagine what would happen if you plugged in, 0.9. At x is 0.9, right? Maybe this is 1.9. At x is 1.1, so just past it, this is 2.1 or something like that. So we're getting really, really close to 2. And I know what some of you are thinking. You're thinking, but look, there's a hole in the graph up here, and f of 1 equals 1. So keep in mind the difference. There is a difference between f of 1 and the limit, or g. So here, if you were to say g of 1, if I asked you to evaluate, which is something you did in pre-calculus, if I said figure out what g of 1 is, well, when you plug in g of 1, either into the, you could look at the graph or down to here, when your x value equals 1, you get 1, and which is exactly what is going on there. So there's a difference between evaluating a function at an x value and taking the limit as you approach that x value, and this is a perfect example of that. All right, moving on to c here, the limit as x approaches 1 of h of x. So again, we're just hanging out at 1 here. On either side, when you approach it, you're getting closer and closer to 2. So here, the limit equals 2. The limit as x approaches 1 is 2 for all three of these examples, regardless if there's a hole or not. So that's just a couple notes. So a hole in the graph has no bearing on the limit. It doesn't impact it, okay? Keep in mind there's a difference between evaluating and finding a limit. And as x approaches c, you're basically asking yourself, what does y approach? What is my y value getting closer and closer to? Next, we just talked about a few of the properties of limits. So just a couple things to keep in mind. Again, this L here is a number, and this M here is also a number. So the sum rule basically says that the limit of the sum of two functions is the sum of their limits. You're kind of allowed to break them up. Okay, so that's what that first property is saying. And then we'll talk about the next ones on the next page. Okay, a few other properties. The difference rule basically just says that the limit of the difference is the difference of the limits. So you'd be able to rewrite this first one as the limit as x approaches c of f of x minus the limit as x approaches c of g of x. And again, from the first page, we know that that was L minus M, so you'd be able to do that, and that's handy. Product rule, again, the limit of the product is the product of the limits. That's all that's saying. The one I'm really interested in is number 4, the constant multiple rule. This is really handy because it allows you to pull a constant out in front of the limit, and that's going to make our lives a lot easier. So we're going to use this one quite often. And basically what it says here is if there's some constant here and you're taking the limit and it's, something times the function, you could take that and pop it right out front and then deal with it later, which that's going to be useful to us. The quotient, and very similar to the product one, right? If you can, as long as you have two functions there, then the limit of the quotient is the quotient of the limits, okay? Just make sure your denominator is not 0 there, okay? All right, so then we talked about some general tips when taking limits. So remember, our limit is a y value. So the first thing you always want to start with is by plugging in the x value to get a y value. This is called direct substitution. That's what that's called. And you're always, always, always going to try this first. This works when the function is continuous, and we'll talk more about what it means for a function to be continuous in the next couple days. But it means that there are no holes or breaks. There's not a gap in the domain, in other words. Okay. So you may have talked a little bit about being continuous in pre-calculus, and then we'll talk about the calculus definition versus kind of the old, do I have to pick up my pencil to trace the graph? And we'll talk about what's acceptable for calculus. All right, so say you try to plug in and something bad happens, okay? So what if when you plug in, you get 0 over 0, okay? You tried to do direct substitution, you end up with something like 0 over 0, or you end up with some number over 0. The problem with each of those, we call those indeterminate forms, is that there is a 0 in the denominator, and we know that that is not good news. So some things that you need to try then is you can factor, see if anything's going to cancel, then you try to plug in again, okay? You may need to use the conjugate to get rid of a square root. So keep in mind that the conjugate and the opposite are not the same thing. Remember, the conjugate of something like x plus 4 would be x minus 4. So you would multiply using conjugates to get rid of those pesky square roots. And some other tips you may need, so this would work. Let's see, if you factored, that would mean that there was some sort of hole in the graph, okay? And you might remember that again from pre-calculus. Remember, if something cancels, then there's a hole, okay? Using the conjugate, that's just kind of an algebraic technique you can use. And finding the y values from the left and the right, that might occur if you have something like some sort of vertical asymptote hanging around that's being pesky. You may need to use some sort of a trig identity, and we'll talk about those at the very bottom of this page, so I'll just hold on to that for a second. And using the limit, any limit properties that we addressed up here, that would be using some of those limit properties. Again, that's mostly algebra. And then using algebra to simplify the expression. So keep in mind positive divided by a negative, fractions, things like that. So I want to kind of give you a tip, okay? When you're finding limits, if you have, so let's say if the limit as x approaches c, and again, that's how you read that. If you have the limit as x approaches c of f of x, if you get that and you end up with 0 over 0, I always tell myself 0 over 0 is a trick. Usually that means that a limit exists, okay? An exception would be some absolute value things. But usually a limit exists here and that this is a trick. So if you get 0 over 0, you need to say, what am I missing? What can I do to get this in a form that I want? So that's just kind of, I'll just put in quotes there. It's a trick. That's not a calculus term. It's a Gueli. Oh, I'll just write trick instead of tricky. Okay? So it's a trick. So do something. Usually here the limit does exist, but you need to do something algebraically or otherwise to make it work for you. All right, now let's talk about these limits of trig functions. Scooch that up here. All right, so for now you're going to memorize these. Later in the year we'll talk about, you kind of will get away without memorizing them. But for now, you'll need to memorize these. They're going to be really handy. So basically the limit as x approaches 0 of sine of x over x equals 1. Okay, the limit as x approaches 0 of sine of some constant x over that x is going to be whatever that is right there. And again, limit is, now notice all of these limits are approaching 0. So if your limit is approaching something else, then you cannot use these. These are only for the limits as they're approaching 0. This one you use a lot here, and what you're doing is just grabbing those coefficients on the x's. You'll end up using that one quite a bit. Some other ones that aren't used quite as much, but I'll put them on there. You have the limit as x approaches 0 of cosine of x. That's going to be 1. And the limit as x approaches 0 of tan of x equals 0. And you could even kind of get these from your head even just by imagining that cosine graph way back from pre-calculus. Remember, our cosine graph looks like this, right? So you could see that the limit right at 0, you were approaching 1 there. And remember, tangent looks like this, and you've got those quick sketch here, those vertical asymptotes. So remember, the limit around 0 would be 0 for there. So those ones, you can always go back to your trig graphs from pre-calculus to know those. Okay? Well, we'll go to the next page. Okay, so it says find the limit if it exists. So again, we haven't really talked about what it means for the limit not to exist yet, so we're just going to kind of take a look at these. So remember, all right, we have the limit as x approaches 1/2 of this. Okay, so our first option that I would recommend is always your direct substitution. So that means you're literally going to take this 1/2 and you plug it in wherever you see an x. So you would just say, all right, well, that's going, the limit there is going to equal 3, and then we're going to have 1/2 squared. So 1/2 squared is 1/4, or you could write it as 0.25, I don't care which. Okay, and then we're going to multiply that by 2 times 1/2, so that's going to be a 1 minus 1. Okay, so then that's a 0, anything times 0, that whole thing is going to go to 0. Now, your answer here can be 0. Now, remember, I did say there was a trick if you got 0 divided by 0, but an answer can be 0. So having the limit equal 0 is perfectly acceptable, and this is a case where that is. And again, we said that this method works when there are no breaks in the graph. And most of you could probably say, just, through some distribution there, that's going to be a cubic, right? And we know that most, cubic graphs are continuous, and they don't have, breaks or holes or anything like that. So this worked because there were no breaks in the graph. And again, you could check that on your graphing calculator if you wanted to throw that in to the y equals. You could do that and take a look at that to confirm that. Okay. All right, again, with that direct substitution, we're going to try this first one here. All right, so direct substitution says, and again, here it's a y value, as y approaches 2. The only reason that this is a y is because the variable in here is a y. So I kind of switched up throughout this page. So the limit, usually we have the limit as x approaches some number. Don't be confused by the variables. Our limit is still a y value regardless of what this is. If you wanted to type this into your calculator, you would just type this graph in as x squared plus 5x, right? Doesn't matter the variable. But I'm going to go ahead and plug in wherever I see a y. I just plug in a 2 there. So it'll be 2 squared is 4, plus 5 times 2 is 10, plus 6 over 2 plus 2. Okay, so with that, let's see, what is that? Oh, 20 over 4, and 20 divided by 4 equals 5. So here, the limit as y approaches 2 is indeed 5. And again, if you wanted to go ahead and graph this and take a look at it, you could. And in fact, if you did graph this and take a look at it, you would probably say, hey, there's a vertical asymptote in this graph. Well, notice that the vertical asymptote isn't at -2, right? Or the vertical asymptote is at -2, but I'm not saying what's the limit at -2. If I was asking for the limit as we approach -2, that would have been a big problem, because when I plugged -2 in there, I'd get 0 in my denominator. That's not the case here, so I was fine, so I'll just make myself a note there. So note, the vertical asymptote was at y equals -2, not y equals 2. And we were taking the limit as y approached 2, so we were good there. All right, so go ahead, try to use some direct substitution in these. You will find that it's going to work well for others and not for some. I'm going to encourage you to pause the video, try to see if you can factor and things like that to take the limits, and then you can come back and check your work, and I'll walk through them. Okay, let's look at a few of these here. So in number 3, you try to do direct substitution first. So you try to plug in x equals 1, and when you plug in x equals 1, you get 0 over 0. So remember, if you get 0 over 0, that's some sort of a calculus trick, okay? We need to figure out what they want us to do. So you go back to the problem, and you're like, all right, what can I do? Can I factor? Well, yeah, I can factor this denominator here. So notice that you carry the word limit down. You don't get to drop this part until you actually plug something in. So I'm still taking the limit as x approaches 1, but now I factored that denominator. Now when you factor that denominator, you can see that the numerator and denominator have a common term, so you can divide those out, or some people say cancel those out. And that still leaves you, notice I didn't drop the word limit, you're still taking the limit as x approaches 1 of 1 over that x plus 1. Now try direct substitution again. That's when I get to drop the word limit. Once I actually plug in x equals 1 there, so I get 1 over 1 plus 1, which is 1/2. Notice how I had to carry that limit down the entire time until I actually took the limit using direct substitution. Okay. All right, in number 4, again, I always try direct substitution first. When I plug in 1, I get 1 minus 1, that's 0. Oh, I get 2 plus 5 minus 7, that's 0, so I get 0 over 0. And again, I'm so sad about that because I just wish direct substitution would work every time. But I guess I'd be out of a job if that was the case. So we take a look then back at the original. I say, all right, what can I do to that? Well, I see that there's a GCF that I can take out of that numerator, so I just rewrote the numerator. And again, I still wrote the limit as r approaches 1. And again, I don't care what variable you use. Usually we use x's, but this is just to show you it doesn't have to be. So I took a GCF out of the numerator. Then in the denominator, I had to use, some of you call it guess and check, others use AC factoring. Either way, you're going to rewrite this trinomial as the product of two binomials. And again, if you're not sure about that, kind of think of how it foils in your head. You'd get a 2r squared minus 2 plus 7 gives you a positive 5, and that'll give me a negative 7. So you could just foil that in your head to make sure it worked. So now that I have this, I'm like, all right, I again have a common factor in the numerator and the denominator, so I can go ahead and cross those out. Okay. So once I cross those out, then I still have the limit as r approaches 1, and I know that that's a pain, but you really want to make sure that you're rewriting that every single time as you go down. Okay, so I have the limit as r approaches 1, I'm left with r over this, and you plug in r equals 1, so you get 1 over 9 as your final answer there. All right, let's look at one that's a little bit trickier. Again, I always try my direct substitution. So I'm like, all right, I plug in a 4 and I get 0 over 0. Darn it, okay? So I'm like, all right, well, I can factor that numerator, but I have a square root in the denominator there, and that square root kind of lets me know that multiplying by a conjugate might work. So the conjugate of the square root of k minus 2 is square root of k plus 2. So I multiply that. I call it an undercover 1, right? Because anything divided by itself is 1. So I'm really just multiplying by a 1, but it's undercover because I want to get rid of this square root. So in this next step, I did two things. I factored the numerator. That's the difference of two squares. So I rewrote that as k plus 4, k minus 4. Okay. And I multiplied by the conjugate, by the numerator and the denominator. So there it is right there. And then in the denominator, that became a FOIL problem. So square root of k times square root of k is just k. Think of it as the square root of k, quantity squared. The square and the square root will cancel each other out. Then here's some radical multiplication. All right, so multiplying radical k times 2 is 2 radical k. Then I have a negative 2 times radical k, negative 2 radical k. And a negative times a positive is a negative, and 2 times 2 is 4. So I've got that there. And again, notice that my limit came down. Do not be lazy and abandon your limit. Otherwise, when we get into more complicated problems, you're going to find that you have all this work on your paper and you have no idea what you're doing because you didn't write your limit. Okay? So now I'm like, all right, well, this and this kill each other off. So that's great, because if I have 2 radical k's and I subtract 2 radical k's, they cancel out. And then, let's see, anything else? Oh, now I'm left with k minus 4 in the denominator. Well, k minus 4 and a k minus 4 those are going to be gone. Okay, so this factor of k minus 4 will end up canceling out with what is left in the denominator of a k minus 4. Okay, so I didn't take the limit yet, so guess what? I'm rewriting it. So I have the limit as k approaches 4, and in the numerator, I don't have this anymore because this, maybe I should grab a different color or something. So this is going to take out those two, okay? And so all I'm left with is k plus 4 times radical k plus 2. All right, well, now I try to use direct substitution again. So let's see, this equals, again, now I can drop the word limit because I'm actually plugging in k equals 4. So 4 plus 4 is 8, and then I have the square root of 4 is 2 plus 2. So let's see, that gives me 8 times 4, I believe, right? 8 times 4. So my final answer there is 32. Okay. All right, we'll go on to number 6. X's and H's. So this one's different. Let's see what happens here. I try to plug in H equals 0. Well, if I plug in an H equals 0, I get x squared minus x squared. Well, that gives me a 0. This isn't looking good so far. Divided by, if I plug in a 0 there, I get 0 over 0. All right, well, I guess what I'm going to have to do is kind of rewrite this some other way, because let's check my other methods. Well, factoring, I don't think by, I can't really factor this. I could rewrite this. I could FOIL that out perhaps, but I don't think anything's going to, that h will still be there. There's no square root, so multiplying by a conjugate doesn't make sense. I could go back to that list of trig rules, but none of those are going to help. So I guess the only thing I really can do here is rewrite this and FOIL it out. So I'm going to try that. Maybe I should write a little smaller on this one. So I didn't take the limit, so guess what? That limit come on down. And I'm going to write this as x plus h times x plus h, because that's what squared means, minus x squared over h. Okay, well, now, what if I actually FOIL that out? Now, let's see, I'd get an x times an x would be an x squared, so that's good, because then this x squared and that x squared might cancel. So I think that that's a good method. So I'm just going to, again, my limit come on down. So I end up with x squared. I'm going to get an xh and an hx. Well, those are the same, so I end up with 2 xh's, or hx's, doesn't matter, plus h times h is h squared, and then I have that minus x squared all over h. All right, so let's see here. This x squared and that minus x squared are going to kill each other off. And then I have, this has an h and this has an h. Well, that means I can take out a GCF. So I'm going to do that all in one step here because I'm running out of room. So we're going to take the limit as h approaches 0. Okay. Notice here that after I canceled this out, I still can't plug in h equals 0 because I still get 0 over 0. So that tells me I had to do something else. So I'm going to factor out an h, and that'll leave me with 2x plus 1 over h. Now I'm in business because this h and this h cancel. And I'm going to go over here. Again, sorry, I have to squish this. I still didn't take the limit, so I got to rewrite. The limit as h approaches 0 of, I'm left with 2x plus 1. All right, now I'm plugging in. So as h approaches 0, oh wait, this is supposed to be an h over here. Sorry. When I take out an h from here, I should have had 2x plus h, because h times h would have given me that h squared, sorry. And so I've got this, and as h approaches 0, if I plug in a 0 there, I'm going to end up with 2x as my final answer. So that's not a number in this case, right? You'd have to have some x value to evaluate it or something, but there's an example of how you would work with limits on that one. Okay, pause there. Sorry about that mistake. Again, when I took out the, when I pulled out an h here, I should have had 2x plus h, not plus 1. Okay, And let's take a look at 7 and 8. And I'm just going to scooch this up. All right. So, again, you always try direct substitution, but negative 2 cubed is negative 8 plus 8. I get 0 over 0. Ugh, annoying, right? That's sad. So what do? I have to factor this. And you're like, how do I factor that? Well, hopefully you remember something, different teachers call it different things. I always called it MOP, or match opposite positive. This is the sum of two perfect cubes. So some teachers I know call it SOAP, for same, opposite, always positive. Hopefully one of those is ringing a bell. Basically what you can do is you can rewrite it. Again, I'm still taking the limit as x approaches negative 2 here. But you have to be able to factor that. So the way I factor perfect cubes, I'm going to factor it into a binomial times a trinomial. And to get the binomial, you take the cube root of this and the cube root of that. So it's going to be an x there and a 2 there. And then you square this first thing, so this goes there. You multiply those two things together, you get a 2x. And then you square that thing, so you get a 4. Okay? And I always call it MOP, so you match. MOP stands for match opposite positive. So I match this sign, so that means this is a positive. You do the opposite, well, the opposite of positive is negative. And then the last one here is always going to be a positive. If you had some spare time on your hands and you wanted to go ahead and kind of FOIL that out or distribute that out, you should get back to this. Okay, so that's how you do that. Now, if you want to work smarter, not harder, one cheater way is to look at the bottom and say, well, hopefully something cancels, so you really want it to be an x plus 2. So that's kind of another way to kind of cheat your way around the system. And so this is going to cancel with that. And then I'm going to use my direct substitution. I'll rewrite it though, why not? So the limit as x approaches negative 2, and this is what I'm left with. And now I'm going to substitute in. So if I plug in a negative 2 squared is 4, and that's going to be negative times negative is positive, so I'm going to get a 4 plus 4 plus 4. So my final answer for number 7 is 12. I've got it just like that. Okay, so there's another factoring technique here. Oh, number 8. This one looks like it's going to be a little tricky. Got to write small on this one. So I see this complex fraction here, a fraction divided by another, a fraction within a fraction, kind of. It's the inception. So I always go to my direct substitution first. I'm going to do my direct substitution off to the side because I think I'm going to need a lot of room here. So if I plug in a 2, I get 1/2 minus 1/2, so that gives me 0 over, if I plug in 2 there, 0. So 0 over 0, that still makes me sad, right? But I always check my direct substitution first. It's a good habit. And now I'm going to have to, I think, get a common denominator here is going to be the only way to do it. So I'm going to take the limit as x approaches 2, and I'm going to have to get a common denominator over here. So the common denominator of this, well, I guess this top fraction would be a 2x, okay? So to get this common denominator, I'm going to say that this is going to equal the limit as x approaches 2. And I'm going to say, all right, to get a common denominator on this piece right here, it needs to be a 2x in the denominator, so I need to multiply by 2 over 2. So I'm going to end up with 2 over 2x minus, now on this piece of the fraction over here, I'm going to need the denominator to be an x, so I need to multiply by x over x. So I'm going to get 1x, or just x, over 2x divided by, and I'm just going to leave that part alone, x minus 2. Okay, so now that I've got that, I'm going to say that that equals the limit as x approaches 2. And I'm going to rewrite it, so 2 minus x over 2x over x minus 2. And you could think of that as over 1 if you wanted to, because then I'm going to do, some of you call it keep, change, flip, something to that effect. So I'm going to rewrite this as the limit as x approaches 2. I'm going to keep this, change to multiplication, and then it'll be 1 over x minus 2 there. And then we'll have to take a look and see, how are 2 minus x and x minus 2 related? Okay, so one thing you might remember from Algebra 2 is if you have something that is a complete opposite. Notice these are not conjugates. Here the 2 is positive, there the 2 is negative. Here the x is negative, there the x is positive. So if they're complete opposites, then you can divide them out and replace it with a -1. So just similar to how -7 divided by 7, you could reduce that to a -1. This term and this denominator here, they are complete opposites, so you can divide that out with a -1. So once you realize that, then you say, all right, well, that's going to equal the limit. Notice I didn't take the limit yet. And I have -1 times 1, which is -1 over, I'm left with a 2x. Now I can plug in x equals 2, and I get -1/4 as my final answer there. Okay, so notice here the calculus we've done isn't actually very much. It's the algebra that seems to be kind of tedious and things. All right, so with that I'm going to go over 9 and 10 down at the bottom here. So remember, if you tried to do direct substitution here, you'd get 0 over 0. That's a problem. But remember, this is on your list, okay? So on the list of things to be memorized. Okay, so we know that from the list that I have. Where were those trig limits? Okay, so again, if you were just kind of sneaking back to that list of trig limits, this example would be just like here. So the answer would be 3, just like that. Okay. Then, if you're looking at this and you're like, oh, well, this isn't on that list of trig limits. Well, that's okay, because our first go-to is always direct substitution. So if you try to directly substitute sine of 0, well, the sine of 0, I did a little cheater graph down here. Let me scooch it up just a tick so you can see it a little better. Woo, hope that doesn't make you nauseous. Okay. So the sine of 0 is 0, so that's where I got this 0 from. So it's 1 plus 0 in the numerator. Cosine of 0, here's my cosine graph. Cosine of 0 is 1, so I got a 1 here. And so you add that together and you're going to get a 1. Keep in mind, you absolutely have to know your unit circle for this class, and quadrant 1 would serve you well as long as you're quadrantals. Knowing the graphs of sine and cosine are also going to be helpful. Okay, moving on to this next one. If you checked your trig list, you wouldn't exactly see one like this. There's not one with sine of ax over bx. There's sine of ax over sine bx. So you're not able to use that. Again, if you try to directly substitute, you run into a problem there. So what I would do is I would say, well, this is the same thing as this is 1 over 3. So I kind of pulled out that third and separated it. And the reason I did that is I wanted to show you that useful property of limits. It was that, I think it was property number 4, that constant multiple rule that says I'm allowed to take this 1/3 and pop it out front. So me doing that allows me to rewrite it like this. Well, now this is on that list of trig identities, okay? So that means it's just going to be 2. So the limit of this part is a 2, and I multiply that by the 1/3, and I end up with 2/3 as my final answer there, okay? All right, and this next one with tangent, again, sorry, you could try your direct substitution, but you're going to end up with 0 over 0, right? So you're like, okay, that's not good. I have to do something else. Maybe you look at that list and you're like, oh, well, that's not on my list, so I need to do something else. So my suggestion here would say, all right, what do you know about tangent? From pre-calculus, you should know that tangent is the same thing as sine over cos, so I'm going to rewrite it as sine x, oop, I'm getting off the page, sine x over cosine x, and that's still over x. So I still got that. And then maybe you can rewrite that complex fraction. So again, I'm still rewriting the limit as x approaches 0. So I'm going to write it as sine x over cos x, and instead of divided by x, I'm going to multiply by 1 over x. All right, well, since this is multiplication, I'm allowed to rearrange these. That's allowed. So I'm going to rewrite it as the limit as x approaches 0. I'm going to write it as sine x over x times 1 over cos x. And why would I do that? Well, this is on that chart, right? Or that's on that list of things to be memorized. So I know what that is. And then I can also say, by direct substitution here, that as x approaches 0, that's going to be a 1. So I'm going to end up with 1 times 1. This is from that list of things to be memorized. And this, via direct substitution, the cosine of 0 is 1. So 1 divided by 1 is 1. So you get 1 times 1. And your final answer there is 1. Okay. You could have done this in 2 steps. You could have said, all right, well, I'm going to take this and rewrite it as a 1 and then, do the direct substitution in a different step. I just did them both at the same time. Okay. All right. Well, there was no things with squareds on that list of things to be memorized. And if I plug in a 0, again, I end up with 0 over 0, so that's not good. So again, I'm always still checking that 0 over 0, but, that didn't work out. So I'm like, all right, what am I left with? Well, I got a sine squared, and my instinct tells me if I have a sine squared, kind of like factoring, I can probably rewrite that as sine x times sine x. Okay, and one of them is over x, and that one's over 1. And we're back to, this is from our chart, that's going to be a 1, right? So you could think of it as a 1, or you could pull it and say, oh, that's a 1, and then factor it out. Okay, so you have 1 times the limit of sine x over 1. Well, plug in a 0 there. Sine of 0 is 0. So you have 1 times 0, which is 0, and you're done there. Okay. All right, the absolute value ones. This one's pretty tricky. You almost have to kind of think about what this graph looks like. Okay. So again, if you plug in here, you get 0 over 0. So you get 0 over 0. That makes me very sad. Let's see, you can't factor it. There's no conjugate, right? So you're kind of like, well, what am I supposed to do with this thing then? So think about the graph, and I purposely put this one as the last one to kind of make you think, well, what does this look like? Okay? All right. Well, I'm concerned about, as x is getting close to 4, so 1, 2, 3, 4, and I don't know, I'm going to maybe, if I plug in, say, you could plug in things near the 4 to kind of get an idea of what this is doing. So say you plug in 0. I like to plug in 0 because it's usually easy. So if I plug in a 0, I get 0 minus 4, you get negative 4. The absolute value of that is 4, divided by negative 4. So you get positive 4 divided by negative 4, you get a negative 1. So you're down at, I might extend this. So at negative 1, you're down there. You plug in a positive 2. Okay, you plug in a positive 2. You get a positive 2 divided by negative 2, which is negative 1 again. Okay? Guess what happens when you plug in a 3? You get a negative 1. And the only problem is when you plug in 4, right? Because when you plug in 4, that's when you get 0 over 0. So what if I plugged in 3.99999? So 3.99999 minus 4 gives me a negative, but it'll be a positive. Then 3.999 minus 4 is a negative. So you have a positive divided by a negative, which is another negative. So at 4, I'm going to put an open circle. Remember, open circle means I didn't actually plug in 4. But it looks like this part of the graph then is just going to be always a negative 1, as long as I plug in something to the left of negative, or to the left of 4 on the number line. Now, what if I start plugging in just a little bit bigger than 4 and anything to the right? Well, so if I plug in 4.1, 4.1 minus 4 is 0.1. 4.1 minus 4 is 0.1. 0.1 divided by 0.1 is 1. So you'll notice that if you plug in anything to the right of 4 on the number line, you're going to get a positive 1. I'm again going to indicate that I didn't actually plug in 4 because I'm using an open circle. So say you plug in a 5. All right, 5 minus 4 is 1. 5 minus 4 is 1. 1 divided by 1 is 1. So this is what the graph looks like. All right. Once you have an idea that that's what the graph looks like, we'll talk about the limit. So the limit is as x approaches 4. So, it's different on either side. How would we indicate that using, proper notation? So to indicate that, we would say something like the limit as x approaches 4. And if I'm coming from the left, so if I'm on this line traveling like this, I'm going to do that by putting this little negative right there. That means I'm coming from the left of f of x. That gave me a negative 1. But if I approach it coming from the other direction, something different happens. So if I approach it coming from the right, so I'm traveling left, but I'm approaching from the right, and I'm going to indicate that with that little plus sign there. If I do that of my f of x, I get a positive one. Notice that these two do not match, and that is a problem. So we say here that the limit does not exist. If the limit never approaches anything, the limit does not exist. And we abbreviate that with DNE. So that kind of brings us into this box here. It says, sometimes we call the limit as x approaches c of f of x the two-sided limit, meaning you have to take into account what's going on either side as you approach the x value from the left or the right. We saw in this case, when you are approaching two different numbers, we say that the limit does not exist. So this in words is basically saying if you're approaching the same number from the left hand and the right hand side, then the limit exists. But if you are approaching two different numbers, then it does not exist. And that's what's saying here. It says if the limit as you approach equals L and the limit from the right equals L and the limit from the left equals L, then you say that the limit exists at L. If that's not the case, then we say the limit as x approaches c of f of x does not exist. And again, we denote that using DNE. Either of those are correct notation. And now we are asked to estimate the limits and the value of the function or explain why they do not exist. So let me scooch this up and we'll take a look at these pieces. Ooh, sorry, it's a little wobbly. Okay, so given this graph here, it says the limit as h approaches 0 from the left. So that little negative there indicates we're coming from the left side. So that means you're moving to the right, but you're coming from the left. And the h value here is 0. So if you're approaching 0 from the left, you're approaching this value down here, which it looks to me is about -4. So we say that that equals -4. Now if you approach 0 from the right-hand side, so you're coming from the right, you're moving left, of 0, then you approach that same -4. Now, because these two numbers are the same, then we say that the limit as h approaches 0 equals -4. So because the left-hand limit and the right-hand limit both approach the same y value, then we say that the limit does exist, and it is -4. Now, what we have here is asking you to evaluate. So notice there's no limit, it's just asking you to evaluate. That's saying what happens if you plug in x equals, or h equals 0. So if I plug in h equals 0, I am at -4 still. So this is what we call kind of the trivial case, where all the answers happen to be the same thing. When we take a look at number 16, that is not going to be the case. So let's see what's going on here. They're asking us to take the limit as you approach 0 from the left. So here's 0, right? So as I approach 0 from the left, so that means I'm moving to the right, coming from the left, my y value is getting closer and closer to that to that 4, so it's a +4 this time. Okay. And now it's asking me to approach 0 from the right. Well, if I come from the right, so I'm moving left, coming from the right, my y value is getting closer and closer and closer to -3. And again, just because it's an open circle there, that has no bearing on the limit. A hole does not affect the graph. So that is approaching -3. So I'll write that down. So then if I asked you, what is the limit as x approaches 0, you'd say, well, from the left it's 4, from the right it's -3, so those two things are not the same, therefore the limit does not exist. So the limit does not exist. Okay? Those two things from the left and the right-hand side have to be equal in order for the limit to exist, and that's not what is happening in there. And now I'm asking you to evaluate f of 0. So if you plug in at 0, which one of these is the true value? Well, this here, I know it's hard to see in here, but this is an open circle down there, and this is a closed circle. So you should have learned from algebra, maybe algebra 2, that the closed circle wins. If you were evaluating this, you would get 4. So this equals 4. Okay. So there you have that piecewise. And we'll take a look at some on the next page. Okay, taking a look at 17 here, again, you've got this piecewise graph, and it's asking us to figure out which of these statements are true and which are false. So A here says the limit as x approaches -1 from the right. Okay, so here's -1. If I approach it from the right, I'm getting that I get a 1 there. And it says they also got 1. So I'm going to go ahead and I'm going to label that one as a true. Okay. And I'm just going to work my way vertically here. So the limit as x approaches 2. So keep in mind, when it says the limit as x approaches 2 and there is no indication of left or right, that means you need to take into account both. So here is x equals 2. So as I approach it from the right-hand side, I get 1. As I approach it from the left-hand side, I get 1. So I would say that the limit there is 1, not 2. They say that it's 2. So I say that this is false. I got an answer of 1. And then we've got, let's see, oh, well, I guess that kind of answers this too. Here, the limit as x approaches 2. We already just said that the limit was 1, so it does exist. It's just, so this is also false up here. Okay? All right, the limit now, D, E, and F are all talking about the limit as x approaches 1. So let's see, as you approach 1, from the left-hand side, so that's part D is asking about from the left, that means you're moving to the right, approaching from the left. The limit is 2. I agree, you're getting closer and closer to there. So this one I say is true. And then when you approach from the right, let's see, as I'm getting closer and closer to 1 from the right, yep, it's going to be at 1. So I agree that this is also true. And so then they're saying that the limit as x approaches 1 does not exist. Well, that is also true because the limit from the left is 2, the limit from the right is 1. Those two things are not the same. Therefore, the limit does not exist. All right, G here. So the limit as x approaches 0 from the right. So from here's 0. If I approach from the right, I'm going to 0. And they're saying it equals the limit as you approach it from the left. Well, from the left when I approach it, I'm also getting 0. So I'm going to say that that's true. And let's see. The limit as x approaches c exists for every c in the interval -1 to 1. So between -1 and 1, okay, not including 1. Notice there's no bracket there. So does the limit exist for every x value in there? Basically that's saying, is this graph continuous during that interval? And that is true. And the last one, it's asking me the same thing, only the interval is from 1 to 3. So from 1 to 3, does the limit exist? Yes, the limit is going to exist everywhere here, even though at 2 there is a break in the domain there, but the limit still exists there. If you were to evaluate at x equals 2, you'd get something different, but we're not evaluating, we're just taking the limit, so this is also true. Okay, so bunch of trues and just a couple falses there. All right, we're going to scooch up and take a look at 18. Now, I'm going to write it out, this time I'm going to write it out as taking the limit from both the left-hand side and the right-hand side, just to get you familiar with that notation and things. Normally, you would just be able to make your concluding statement. Okay, so I'm going to pause and kind of write down some stuff, and then I'll join you back in just a sec. Okay, so they're asking me to take the limit as x approaches -3. So what I'm going to say is, here's x is -3. So from the left, I'm approaching it from the left-hand side of -3. My limit there is going to be 4. So the limit, as I approach there from the left, that's what that little negative indicates, I got a positive 4. Now when I take that same limit, approaching -3, but from the right-hand side, so here's -3, so if I approach from the right-hand side, I'm getting closer and closer, my y value is getting closer and closer to -2 there. So then I'm going to mark that down as a -2. Well, notice that 4 and -2 are not the same number, so we would therefore, that's what those 3 dots mean, so therefore the limit as x approaches -3 does not exist. So you can say equals DNE, or you don't really need the equals sign there, you could just say it does not exist, because the left-hand limit and the right-hand limit are not the same number. All right, now we're going to approach -1, so here's -1, so the limit from the left is 1. The limit from approaching from the right is also 1. So if you're 1 from the left and you're equaling 1 from the right, notice those two things are the same. So then we say the limit does exist and it equals that number. and now we're approaching 2. So, back to part B though. If I asked you to evaluate what is f of -1, f of -1 would be 3. So notice that when you evaluate the limit somewhere, it doesn't necessarily have to equal the, or when you evaluate the function, it doesn't have to equal the limit. That's going to mean something else once we get into a little bit more about continuity. Okay? All right. So here we're at 2, so we're approaching 2. So here's the x line of 2. And I know for some students it helps them, whatever you're approaching, so if it was 2, I've seen some students kind of do this. They like put a little dot down there, and they're like, okay, now I need to say from the left I'm going like this, from the right I'm coming like that, and that kind of helps them visualize it. So from the left I'm getting closer and closer to 1. From the right I'm going to approach from 1. And since they are both 1s, that is a winner, and we'll say that the limit there is also 1. Okay. All right. I'm going to fill in the answers for number 19, so you can pause the video and then start it again when you're ready to check your work. Okay, so I went ahead and put in the answers for number 19. Hopefully you got them all correct. And then there's just kind of one last thing I wanted to show you. Sometimes you'll see in a textbook, or I've seen them give you problems where they're asking you to take a limit or to evaluate a limit by looking at a table of values. So let's take a look at this function f of x here. Now remember, we know the answer to this because that was on our list of ones we had to memorize. So the answer is going to be 1. But let's just take a look at how it would look on a table. So note that AP rounding is always to 3 decimal places. So for this class, from now until forever, we will be rounding to 3 decimals. The only exception is if it is money or if it specifically asks you to round to the nearest, person or something like that. But 3 decimals is AP rounding standard. And so in my calculator, what I did is I went to the y equals, and I don't know if this is going to show up very well. So I went to y equals, and I typed in the function, and your calculator needs to be in radian mode. 100% of the time for this class, your calculator will always be in radian mode. So I typed it into there, and then you can look at the graph. So you could do a zoom, zoom trig if you want to kind of take a look. And there's the graph. And then I wanted to evaluate the table. So you could look at the table, and I gave you some tips on the next page on how to adjust your table. Or you could do second and then the trace key and then just type in value. So I did, the first value on there was a -1, so I just typed in a -1 and hit enter, and that's where I got that 0.841, and I rounded to 3 decimals. So I went ahead and did that with the rest of them, and I got this as my table of values. And as you can see, it is getting, closer and closer, and then once you round it, these are, 0.999, so once you round, they all become 1s, okay? So very similarly, I started doing the same thing, only I approached it from the right-hand side. So I started plugging in values just to the right, and you'll notice the very same thing happened. As I got closer and closer to 0, my value got closer and closer to 1. So that's just, I wanted just to see an example of you kind of finding the limit looking at the table. So if you're given the limit from a table, you'd want to look at the table and see, as you're approaching from the left, what are you getting closer and closer to? As you're approaching from the right, what are you getting closer and closer to? And again, this is 1, and we knew that because it was on our list. So let's just talk in closing, and we'll finish off with some notation, and that'll be it. So here we say that because f of x approaches the same value from the left and the right, we say the limit of f of x as x approaches 0 is 1. And in math, you would write it this way: the limit as x approaches 0 of f of x equals 1. These two things mean the exact same thing. One is in words, and one is kind of written in mathematical terms. So in general, how do we talk about limits? So you say the limit of f of x as x approaches c, or pick your favorite variable, equals L. Sometimes you see the word is there, so is or equals, either is fine. And again, how do you write that in math? It's going to be the limit as x approaches c of f of x equals L, and that's how you write it there. And of course, if you approach a different value from each side, if your left-hand limit does not equal your right-hand limit, we say that the limit does not exist. Okay, so we say that the limit does not exist. Does not exist. In other words, DNE. Okay. So we've got that. Just in closing, keep in mind today that your limit is a y value, okay, that the function approaches. And when computing limits, always try to plug in the x. And when you plug in, you get if you get 0 over 0, you're going to have to try to simplify. And next time we're going to look at what happens when you get a number over 0. All right, that's it for today. Stay tuned for Unit 1, Day 2. That'll be a separate video. Have a great day.